Hello guys, good morning. So today we will be discussing some ductility concepts and beams. And this course covers some relevant principles in reinforced concrete design behavior uh, within the elastic range of response, but requires some nonlinearity property of the material and the geometry of the member. So before we proceed with some ductility concerns, we need to define first three very important terms, which are strength, ductility, and toughness. Okay, so while these three are actually related to each other, we have to realize that when we talk of strength, we just simply uh, are concerned with the resistance, no, of the member without failure. When we talk of ductility, we are focused on some characteristic of the member prior to collapse, and that is the manifestation or undergoing of some or very large deformation before it fails. So, in the ductility part of the definition, so the nonlinear range of behavior is actually met, no? Which is the same also on toughness, wherein the only difference between the two is on the cyclic behavior of the member. So when we talk of ductility and toughness, we simply are referring to the range beyond the elastic, okay, beyond the elastic uh, domain, and this property together with strength are very important to okay to ensure that our behavior from elastic to the inelastic range are connected, no? uh, if the elastic and the inelastic range are related in such a manner that the manifestation of the behavior is defined within, or yes, within some range of elastic and inelasticity, then we can say that uh, your your beam design constitute these three important properties to resist loads coming from earthquake, maybe earthquake, wind, and other vibration loads. So these considerations, of course, have to be met with all the limit state conditions like flexure, shear, axial compression, axial tension, torsion, etc., or combination thereof. And the number of limit state will depend on the designer, the way the designer sees the value of it. Some give importance to flexure, some gives importance to shear, depending upon the type of the member, or the type of behavior that is expected in the member. So today we will be only focusing on the limit state condition wherein the flexural behavior is being met. And we start with defining some behavioral terms like curvature, which is defined as within this in this figure as simply this angle upon which this elastic curve is drawn by subtending two lines, okay, creating a point of or a center or a point of rotation there. So the angle subtended by these two lines at points within the ends of this beam, or sorry, the supports, location of the supports defines your phi1 here, and from the right support to the free end defines another curvature, which is say phi2 there. So the relationship between this deflection and its derivative may be noted below in our elementary mechanics as EIY, but we are more familiar with this moment, okay, equation. Okay, it's the moment equation is given by this differential equation, which is the second derivative of your displacement or deflection, and this is actually the part here, which is m over ei, is actually the curvature that we are talking about. Okay, so if we divide the moment with this flexural rigidity there, so this is what curvature is all about. And differentiating it more, or twice rather, will yield to the shear and the load equations, and integrating it twice will yield to the slope and deflection. So this is the basis for our double integration method that we have been using to solve for deflection. Note that the degree of the curve for a particular variable is 1 degree less than the other starting from the deflection, while the derivative is 1 degree greater than the exceeding variable starting from deflection. So in the ductility of beams now, we relate these equations in a way that the equilibrium condition for the internal forces should be satisfied. So if we want to solve for the ductility, or to measure the ductility, we need to convert these curvature equations into an internal curvature, which is simply defined on the basis of your strain, okay, diagram. So this angle here is actually the curvature, the same as the curvature that is being uh, discussed here in your elastic curve. Okay, so if we cut, let's say, the beam here and some get the original slope of this there. So we have here a representation of the curvature phi, uh, which is simply subtended from this line to this line. Okay, so this is actually the phi that we are talking about here. So this is simply what? Is simply the strain diagram at this particular section. So at any particular section, the curvature is different, okay, depending upon the loading condition, etc. So this curvature now that we are talking here about can be expressed in terms of the strain all over the distances from the neutral axis. Okay, so if we want to get the curvature now at this point, we simply get the value of the strain and this value of c here, we divide it So phi is simply the tangent or the arctangent of the angle, sorry, the arctangent of this value epsilon c all over c, or simply for small angle the phi is actually approximately equal to tangent phi, which is simply epsilon c all over c. Okay, so this same curvature uh, is defined in terms of the internal strain relationship, which is the same as this uh, elastic curvature defined in terms of our elastic curve diagram. Okay, for the equilibrium conditions, we know that C equals T and A is defined in terms of beta 1C. We can now come up with some uh, mathematical formulas using simply uh, this relationship, okay, such that if I want to get the the uh, the maximum steel ratio to ensure a ductile mold of failure, so this is actually simply the maximum ratio, which happens to be your limit for ductility in beams. Okay, so the 75% or 0.75 there is simply a factor of safety of 1.33 given um, to the beam to ensure a ductile failure. Okay, if we divide the raw balance by 1.33, it will give you 0.75 raw balance. So the rest are actually very familiar formula, and this raw minimum, which is a derivative of the the cracking limit of your beam, okay, from an uncrack. Okay, so this is an crack stage to a crack stage is given by this. The derivation I have not introduced here, but this is a very familiar formula, and it has to be compared with the 1 over 4 square root of fc prime over fy to ensure uh, that the beam will behave in a ductile fashion. So within this range of raw minimum and raw max, raw must be in between to ensure a ductile failure. Okay, so that's it for the ductility conditions. So we continue on moment curvature relationship in the next video. Thank you very much.